All right, let me make some space here to put this file, and I'll open it up. I can go to meetings telling me I got to upgrade from my Windows version to a new. They're not going to support Vista anymore.
Oh, that's good.
No, that's not good at all. I'm not looking forward to it, and I've only got till April 1st to do it. And I know you have to do a clean upgrade. In other words, you have to reinstall everything.
Ugh, sounds like a pain.
It's not going to be any fun. All right, here we have a special kind of cubic. And by a special kind, there are some cubics that are relatively easy to solve if the ratio of the coefficients for the first term and the second term is the same as the ratio of the coefficients for the last two terms. In other words, I've got 1 is 1 over minus 4, the same as minus 7 over 28. And it is, which means we can solve this the easy way by grouping. Okay, I'm going to group those together, and I'm going to group the last two together, but I can't put a parenthesis around those two without changing the sign on this term, right? In other words, if I want to do that, I can only do it if I change that plus 28 to a minus 28. Because now, if I remove the parentheses, it would be back to where I started from. That's what you always want to make sure. You never change it when you add, and this is the easiest mistake to make when you're grouping, is to forget to change that sign. Okay. Now factor each one. What's the greatest common factor on the left?
X squared.
And leaving
X minus 4.
And what's the greatest common factor on the right?
7.
Leaving
X minus 4.
Now, the reason this works is because I can now factor out an X minus 4. And this is something that's probably new and different to you. In other words, your entire math career, you've always factored out individual terms only. Or maybe a 2x squared or something like that. But not very often have you ever factored out an x minus 4. Well, I can do it. And what am I left with?
X minus 4 and x squared minus 7.
And now I can actually use the difference of squares to factor the x squared minus 7. Although you don't really need, it's the safest way to do it. I mean, there's a couple of ways to find the additional factors of this, but notice that I can use the difference of squares, even though the first time you learned it, it was called difference of perfect squares, right? Well,
yes.
This is not a perfect square. However, it doesn't have to be perfect. This factors into x minus square root of 7 times x plus square root of 7.
Okay.
And those are my 3 zeros. So what am I, the first question here is to find the number of possible positive real zeros. How many do we have?
2.
3.
3?
Well, all 3 of these multiply to 0. In other words, we start by setting that thing equal to 0 if we're looking for the zeros. And what
Okay.
we're going to do is factor it all the way down, and here are the 3 linear factors. Just because these are irrational numbers doesn't matter. We still get 3 zeros. X equal 4, x equal positive root 7, and x equal negative root 7.
Okay.
Root 7 is what? Approximately 2.3 or something like that? So
Yeah.
we have 3 real zeros. What we actually have is one rational zero and 2 irrational zeros. And these irrational zeros almost always come in pairs. If I were to use the quadratic formula on that to break it down, I would have gotten plus square root of 7 and minus square root of 7. Okay.
Okay.
Let's see. What's the rest of this question say?
I also have another question because my teacher did it a different type of way, and I want to know if you understand how to do it this way as well.
Well,
I mean,
you always use this way if you can.
Okay.
Because it's far easier than the other way. And we'll get to the other way. In other words, list number 2 says list the possible rational roots of the function. And that is using the rational factor theorem, which is what you're talking about. In other words, if this did not lend itself to grouping, and you can see that that's not going to happen very often, where the ratio of this coefficient to this coefficient is exactly the same as this to this. So grouping is very unusual, but when you see it, you use it. I'm surprised he's using this as an example for the rational factor theorem, other than the fact that we know we can solve it the other way also. But the rational factor theorem says the following. If this function has a rational zero, its numerator has to be a factor of the constant, and its denominator has to be a factor of that coefficient. In other words, the numerator has to be a factor of whatever this number is, and the denominator has to be a factor of whatever that coefficient of the lead term is. Okay? Now let's talk about factors of 28. What are they?
7, 4, 1, 28.
To make sure that I get them all, I like to do it this way. Start with 28 and 1, because those are 2 possibilities. And then cut that in half if you can, and double that. And then do the same thing. Cut that in half and double that. Now, I've got them all. Okay? So, what that means is that my numerator can be plus or minus 28, plus or minus 4, I'll list them in numerical order, plus or minus 7, plus or minus 4, plus or minus 2, plus or minus 1. My denominator has to be plus or minus 1. So basically, I can ignore the denominator in this problem. If this had a 2 sitting right there, then my denominator could be either 2 or 1. If I've eliminated it to 1 only, this case, then I can just erase it. Those are my possible rational factors. You remember when we solved it, we came up with 4. Okay? So, list the possible rational roots of the function. Each one of these is one of them. There are 12 of them. The reason you use plus or minus with every one of them, regardless of the sign. In fact, the sign is not important on this. Because all we're looking for are factors of the number 28 and it's always going to be plus or minus. The reason is that when I came up with 28 and 1, that could have been minus 28 times minus 1. So that's why all of them are plus or minus. Now, here's the hard part, and this is the reason this is such a difficult technique. If this is the only technique I have for solving this, then I have to, by trial and error, go through each one of these. And I can do it using synthetic substitution or synthetic division. It's the same thing, synthetic substitution or synthetic division. And I always start at the bottom. I try both of those. I would not get a zero remainder. I'm looking after my synthetic division, I'm looking to get a zero remainder. If I do get one, I'll know that is a zero. Okay? We'll also remember that we only had one rational zero on this function when we did it the other way. The other two zeros were irrational. So they're not going to show up here. We know that only one of these 12 is the zero. But if I didn't have this other technique, that's how I would proceed. And when I got to plus 4, I would get a remainder 0. Now, do you have any questions about synthetic division?
No.
Okay. And you're familiar with the zero remainder theorem?
Not really.
Well, let's do this one, knowing what the answer is, so I'll know what to synthetically divide it by. If my 0 was at 4, which it was, then that's what I want to put in the box, is 4. Okay? My linear factor was x minus 4, which made the 0 4. You with me?
Yes. Oh yeah, my teacher said I can use a calculator to do this as well.
Well, just by the nature of the questions, that will not really help that much, but let's just make sure we do one of them, just so I can show you what I'm talking about here.
Okay.
In other words, what you need to learn is this zero remainder theorem. That's very important, okay? So I'm going to synthetically divide 4 into the coefficients of my cubic polynomial.
Okay.
And if 4 is one of the zeros, then I will get a 0 as my last term right there.
Mm-hmm.
So you want to help me with the synthetic division?
Okay, there'll be a 1 on the bottom first. Then it'll be 4. Then it'll be 0, 0, negative 7, and negative 28, and I'll bring it to a remainder of 0.
And that's what you need. Not only does that tell me that one of my factors is x minus 4, but it also gives me my other factor. That is x squared minus 7. No middle term, no x term. And so I can get to this step. But notice that it would be my 5th step. In other words, I would have already tried dividing by 1, then I would divide by minus 1, and then plus 2, and then minus 2, and then plus 4, and I would have found it. Okay? And once you find one solution, that resolves the problem, because what you're always left with is one level less polynomial. So if I can get this thing down to a quadratic, I'm home free. I've got a quadratic formula I can rely on, always to factor that.
Okay.
Okay, so this, you can see, is a brutal technique. They're never going to give you more than one of these problems on a test because they take about 20 minutes.
Mm-hmm.
And that's why I did it the other way. I mean, grouping was a whole lot easier. Look how quickly that happened, and I got to the answer in 2 or 3 steps in about 30 seconds, as opposed to this way. I mean, who knew that it was this hard to factor a cubic? Most people, they get to the quadratic formula and they say, this is as hard as it gets. But it's not even close. Using possible rational roots is way harder. Determine the rational zeros for the function. We've done both of those. So we've actually done this problem from all directions.
Okay.
So I think we can go on.
So would that be x plus 4, x minus 4, x minus 4i, and x plus 4i?
Uh-huh. X plus 4. X minus, woo. It's either a typo or they intentionally left off one of the zeros. I'm thinking it's a typo. And here's why. Imaginary solutions never come one at a time. They always come in pairs.
Come together, yeah.
If minus 4i is a solution, then plus 4i is a solution.
Okay.
So if this is not a typo, then here are my 4 factors. Okay?
Okay.
If I multiply those 4 things together, I will have a polynomial function.
Correct.
With real coefficients. Which 2 am I going to multiply together first?
X plus 4 and x minus 4.
Well, I can immediately get rid of the complex numbers by multiplying that by that. Notice that that's the difference of squares already factored, right? So I know
Yes.
that I can multiply that really quick. It's x squared minus 16i squared. Notice that if you started with that, you'd factor it into x minus 4i and x plus 4i. Okay? And the beauty of multiplying these two things together is I can convert that I squared. What's minus 16i squared equal to?
Minus 16i squared, 4i, and
I squared is minus 1.
minus 1. Okay.
Which means minus 16i squared is plus 16. So after I've multiplied these last two together, I get this. It's not 16i, it's 16. In other words, I'm replacing the I squared with a minus 1. And don't forget that process. That's a very common practice.
Okay.
You always do that. Whenever you see an I squared, you replace it with minus 1.
Okay.
Now, this is also difference of perfect squares. So I happen to know that this is going to multiply it back into what? The first two.
X squared minus 16.
So now we have a binomial times a binomial, which also is difference of perfect squares, which I'm sure all of, oh, excuse me, that is not difference of perfect square. Yes, it is. Yeah, in other words, that's the difference of perfect squares. What did it start as?
Plus 4 and minus 4.
X to the 4th. Remember, if this is the result of difference of perfect squares, then we need to square that number to come up with this first number. And the middle number is minus, what's 16 squared?
256.
There is the polynomial that they seek. And
Okay.
assuming that they just neglected to give us the second or the fourth zero. There's no real clue. They don't tell us it's a fourth degree polynomial or a third degree polynomial. This might, if it's a typo, then there's only 3 zeros, and they are -4, 4i, and -4i. But the one thing I know for certain is that you cannot have only 3 zeros and only have one of them be complex. You can have only 3 zeros if it's a cubic. You're going to have the same number of zeros as you have degree polynomial most of the time. But complex ones have to come together. So this answer is only if the fourth one is 4i. If it's not, we can't really do the problem.
Okay.
Because, all right, so we're using this function, which has all degrees of x and a constant. It's useful to know. Write the function as a product of linear and irreducible quadratic factors. Now, you can't use grouping in a quartic. That only works with a cubic. Wouldn't have worked here even if you take away the x to the fourth. So, wow. The question is, how does he want you to do it?
I think this is what you're saying about the calculator.
Here's what the calculator is going to do. Here, let me use my Wolfram alpha, and I'll show you.
Like finding the zeros on the y.
Right. In other words, that is going to be a tremendously difficult task if we have to use the rational factor theorem. But if we can use a calculator, then it'll point out the whole number of zeros. And I'm betting there's going to be quite a bit of them. And probably 2 of them. Once we find 2 zeros, we'll divide it by each of those zeros, and we'll be left with a quadratic, which is probably going to be an irreducible quadratic, since it kind of warned us of that. The beauty of Wolfram alpha, I don't know if have I showed you Wolfram before?
Yes.
Yeah, it shows you what you typed in. And so you have a way of checking it as opposed to a TI-84, which doesn't show you the function. So we typed it in correct. And I can see there's a 0 at 3 and there's another one at -2. And Wolfram alpha even gives us the zeros. Well, there's the 2 real roots, -2 and 3. And we're left with a quadratic that produces 2 imaginary roots. But let me go through this. So, knowing what 2 of the real zeros are allows me to do what? In other words, I know that there's a 0 at 3 and a 0 at -2. Therefore, what are 2 of my linear factors for this polynomial? In other words, it wants me to write it as a product of linear and irreducible quadratics. What are the 2 linear factors? Remember, I know that x equal 3 is a 0 and x equal -2 is a 0 from the Wolfram alpha.
So, I would have to find another factor.
No, work backwards. If I came to you and I said that x -3 times x plus 2 is equal to 0, what would have to be true?
X squared.
No, hold it. Don't multiply it back together again. In fact, a lot of times it takes a lot of work to get it factored. The reason we want it in factored form is because you cannot multiply two numbers together and get 0 unless one of them is 0. So when I get that in that form, I'm able to say, okay, that means that x minus 3 is equal to 0, or x plus 2 is equal to 0, which makes x equal 3 or x equal minus 2. So if they start by giving you the zeros, you have to turn that back into those two factors by going the other direction. Okay? You with me?
Oh, so okay, I see.
Yeah, in other words, you always make this x minus 3 and x minus a minus 2, which makes it x plus 2. All right.
Okay.
There's two of our factors. Now, in order to figure out what the irreducible quadratic is, we need to divide this thing. And let's do it synthetically, real quick. So what goes in the box? What's the first step here? Let me put the coefficients across the top. We have a 1, we have a minus 1, we have a minus 2, we have a minus 4, and we have a minus 24. It's the first number that's going to go in the box.
So
One
would
of
it be
our known zeros. Pick one. It doesn't matter. Doesn't matter which one, because you're going to do it twice. In other words, and whatever answer we get from this, we know we're going to have a remainder of 0, and we know what's left over below the line is the cubic, which we're then going to divide by 3. Which is going to give us the irreducible quadratic that they want. Okay. Make a little bit more room here. Let me take that 0 out. We'll find it, but I'll do it real quick. I know you know how, so I don't need to test you on it anymore. There's our 0. There's our cubic. In other words, if I were to take this polynomial and divide it by x plus 2, I would end up with a cubic. But what we're going to do is divide it by the other known 0. That also produces a 0. So we have our two linear factors, and this is the quadratic. What is that quadratic?
That'd be x cubed.
No, we've divided it twice. Every time you divide it, you
X squared.
Right, you reduce it by 1.
Plus 4.
And that is called an irreducible quadratic because it only factors into imaginary numbers. So they're not really interested in the answer having the imaginary numbers. And so usually the exercise with these things is to always factor it down to its linear factors. And these are the two linear factors. And its irreducible quadratic. Instead of x minus 2i and x plus 2i.
So what would I do with the quadratic of the negative 2?
With the what?
The negative 2.
Well, I divided by that 0. And that represents that linear factor.
Okay.
The 3 represents this linear factor. And what's left over after you've divided by those two linear factors is your irreducible quadratic. In other words, the goal on all of these is always to get it down to its linear factors and a quadratic. Whether you want to reduce it further or not doesn't really matter. I mean, this might be something like x squared minus 4, in which case I could factor it down to its linear factors also. But you don't want to take this down to linear factors that have complex numbers in them. Just,
Okay.
it's not useful to have complex numbers when they're not necessary, and so we take it down to an irreducible quadratic. And when she said it was okay to use your calculator for this, she meant,
Yeah.
I guarantee you, she meant it only in the sense of finding your first two zeros. She didn't want you to see these complex roots, which if we put those back together again, we come up with the x squared minus 4, or x squared plus 4. And so we could have saved ourselves a lot of work by just multiplying these two factors or zeros back together again to come up with that irreducible quadratic. But I'm quite certain she wants you to do it this exact way, which is to divide by one of the zeros that we got off of our graph, divide that result by another zero that we got off of the graph, and you're left with the quadratic.
Okay.
In this function, I'm going to leave Wolfram F. Write the function as a product of linear factors. In other words, now they want you to write it with all four factors. Take it down to not an irreducible quadratic, but how does that quadratic factor? In other words, that's not linear. That's quadratic, meaning there's an x squared term. Well, as we saw from Wolfram alpha, it factors into x minus 2i and x plus 2i. Now I have the thing down to all four linear factors. Even though two of them are complex, that's what it asks for. This is the answer to the first question. This is the answer to the second question. Number 6, list all of the function's zeros. What are they?
Plus 2.
No? Always the opposite of that sign.
Oh, so negative 2, 3, and then plus or minus 2i.
Actually not. X equal 3 is one zero. X equal minus 2 is another zero. But imaginary numbers aren't zeros. They do not cross the x-axis. As you'll notice, if we look at that Wolfram alpha, it only crosses the x-axis in two places, there and there. And the reason we have two pictures here is one of them is zoomed out and one of them is zoomed in. Okay. But both of them can show you that it only has two zeros. So remember, complex roots are not zeros. They do not cross the x-axis. In the same way that if I gave you the quadratic, x squared plus 4, and said, where are the zeros of that? You'd draw a parabola, but you'd shift it up by 4, right? And it would look like that?
Yes.
Notice that does not cross the x-axis, and it has no zeros. Has no zeros. If I set that equal to 0 and try to solve it, I get an imaginary solution.
Okay.
Okay. It's actually funny. The entire problem was done in number 4. Well, not really. I guess you had to break down the x squared plus 4 to get number 5. Is that it?
Yes, for this one. I have another one.
Okay. Can you verbalize it?
I can send it to you, actually.
Okay. Go ahead and do that.
One sec. Okay, I just sent it.
Same title.
Yes.
Okay.
Wait, is this different? Or wait, did I send you the same one?
Well, maybe, or I bet you sent me the same one because it shouldn't have the same title, should it?
Because there's a number 2 and a number 1.
Okay. Let's see. If I go back and look at the first file you sent me, it was 2.4 homework.pdf. This a different PDF file?
I think so. Just look at the first problem and then we'll know for sure.
Well, when I opened it up, here, if I open both of them up, this is the one you just sent me because it has a 1 next to it, meaning it's a copy.
Okay, so then I already sent you that one. Okay.
Yeah,
I'll send you another.
it's the same function, I believe. Yeah.
Okay, I'm re-emailing.
Yeah, same date. These are identical to one another.
Okay. Now I sent the correct one.
Okay. Whoops. Okay. Find the number of possible positive real zeros. Well, let's graph it. Because at this point, we know that it probably has there's 4 zeros. You don't have to have 4 zeros because some of them can be complex. In other words, we might have 2 real zeros and we might have 2 imaginary, like the last problem. So right off the get-go, we don't know the answer to this. But if I graph it, and if she says that's okay to do, well then let's do it.
Okay.
That'll get us started. In fact, that's almost the only way to get started. Because the other way involves that rational factor theorem, and that just takes all day long. Let's see, there's a +2 in front of that. And then we have minus 6x squared. So I'll change that to a 6. And minus 6x. And plus 9. Yeah, Wolfram Alpha also is better than a normal calculator because it gives you all the zeros without you even asking for them. Okay. Here are the 4 roots. You can see that we have 2 rational roots, and you can see that we have 2 irrational roots. And irrational roots are a lot like complex roots in that they always come in pairs. I think. I'm 99% sure of that. I think they always come in pairs. So if I look at the graph, How many zeros are there?
2.
Everywhere it crosses the x-axis.
Oh, 1, 2, 3, 4. 4.
3 and 4, and this shows 4 also. 2 of them are real, or 2 of them are rational, and 2 of them are irrational. But irrational doesn't mean, crazy. It just means it's on the number. It's on the real number line. It just means we can't represent it by a fraction. So the answer, find the number of possible positive real zeros. Positive real zeros. Well, there's only 2 of those. These 2 are negative real zeros. The number of possible negative real zeros. So we have 2 of each. List the possible rational roots of the function. They are not going to let us get away from that, huh?
Nope.
No, they're going to just force us to go through that tough so tell me how to do it again. If my function is, okay, read it from where it says the input there. No, that's not too bad. What's the rational factor theorem say? That if I have a rational factor, what will be true?
It's a rational factor.
Its numerator will be what?
A whole number, irrational.
Factor of 9. It'll be a factor of the constant. Well, if we list the factors of 9, there they are. Okay, so my numerator has to be either plus or minus 1, plus or minus 3, or plus or minus 9. My denominator has to be plus or minus 1, because that's the coefficient of the highest degree. It's the only thing that matters for determining this by the rational factor theorem. You hear it referred to as P over Q. Okay, where P is a factor of the constant and Q is a factor of the coefficient of the largest degree. So here's our possible, those 6 possible rational factors. List the possible rational roots. So these 6 numbers is how you want to answer that. And notice that is 6 numbers, not 3.
Yes, plus or minus.
Right. Determine the rational zeros for the function. Well, if we do it the hard way, we're going to, by trial and error, divide each of these 6 possibilities into the original polynomial to see if we get a 0 remainder. When we get a 0 remainder, we will know we will have found one of them. We will keep trying the rest to see if we can find more than one. After doing all of that, clearly, with the help of Wolfram alpha, we see that minus 3 and 1 are zeros. So if we'd have gone through this 15 or 20 minute process, we'd have come up with, we got a 0 at minus 3, and we have a 0 at 1.
At 1.
Now, once we do the synthetic division, and we take our 4th degree polynomial, and we divide it by each of these 2 known rational factors, we will have left a quadratic. Right? In other words, we start with a quartic, we divide it by 1 linear factor, we're down to a cubic, divide it by divide that by the second linear factor, we're down to a quadratic. And
Yes.
then actually it's a quadratic that has real solutions. We know that because crosses the x-axis 4 times. So we know it has 4 real zeros. It's just that the other 2 are irrational. So you're never going to find these 2 using this rational factor theorem. But you don't need to. In other words, obviously the remaining quadratic is going to be x squared plus 3, or minus 3.
Okay.
In other words, after we go through this whole thing, we're going to have x plus 3 as one of our factors. You see how I get that from that?
Yes.
And we're going to have x minus 1 as another one. And then we're going to have that. Well, in this case, that is not an irreducible quadratic. We can reduce that. It's only irreducible if it has complex solutions. Well, this doesn't. This one reduces to x minus square root of 3 and x plus square root. And so there are our 4 linear factors.
Okay.
Hold on, I'm trying to find the next part of their question. Determine the rational zeros, which were minus 3 and 1, right?
Yes.
And determine the irrational zeros, which were square root of 3 and minus square root of 3. Determine all of the zeros. Well, that's the rational ones plus the irrational ones. And so all of the zeros are these 4. These are the 4 linear factors. Those are not the zeros. The zeros are minus 3, 1, square root of 3, and minus square root of 3. Those are the 4 zeros.
Okay.
Write the polynomial function. Oh man, they did exactly the same thing. He put 2i in there. Well, at least now I'm less inclined to think that it's a typo. He's just omitting the minus 2i.
Okay.
Okay. So they're really, whenever they give you one complex solution, they're always giving you 2. So they'll only give you 1, but they're leaving it up to you to know that minus 2i must be another one. So how am I going to get this polynomial?
It would be x plus 2, x minus 1, x minus 2i, and x plus 2i.
And
X squared minus 4i. Wait, hold up. Yeah, x squared minus 4i.
which converts to actually x squared minus, it's x squared minus 4i squared.
4i squared. Then that would become a negative 1, so that would be x squared minus, or plus 4.
And there's your irreducible quadratic. And then this becomes x squared plus x minus 2, which is a trinomial. You know how to multiply a trinomial by a binomial?
No, I
Because to
don't.
come up with a polynomial, that's what we need to do here. They may have taught you something called FOIL, which works great on binomials times binomials, but it doesn't work at all on anything else.
Oh, really?
But what I call ET, which works for quadratics, and it also works for everything else. And what it means is every term by every term. and do it in a pattern that you can follow. In other words, take the first term, multiply it by that. Take the first term, multiply it by that. Take the second term, multiply it by that. Second term, multiply it by that. Third term by that. Third term by that. So what do we have? First one is x to the fourth. Let me erase all of those things and let you come up with the answer.
Okay, so it'd be x to the fourth plus 4x squared.
Hold on. Oh, excuse me, my fault.
Plus x cubed plus 4x minus 2x squared and minus 8.
So it's the same as FOIL. FOIL is also every term by every term. I don't know why, they name it FOIL. And now we have to simplify this. And we can generally simplify this because there's only going to be one x to the fourth term, and there's only going to be one constant. But the stuff in between, notice that we've got some other stuff. So we have a net 2x squared, and we have a plus x cubed. And we have the x to the fourth, and plus 4x minus 8. And that took care of everything. So there is the polynomial that they seek. Write the polynomial of least degree. That's what it is. Fourth degree polynomial.
Okay.
Notice what we can do on number 4.
Rank functions product.
Well, it's got that ratio is the same. So I could actually solve this one rather quickly by grouping it. Now, that's going to allow me to answer number 4. It's also going to allow me to answer number 5, and it's going to allow me to answer number 6. So there's no reason to do this the hard way. Let's do it the easy way. It'll take you about 2 seconds. Well, 2 minutes. Tell me how to do it.
Find factors for 27.
First of all, you got to combine parentheses. And we're going to put those two together. Now, the only reason I didn't have to change any of the signs was because that's a plus. Had that been a minus, I would have needed to go in and change that sign right there to a plus. But right now, what I've written is the same as what was written originally. Now, what's the next step?
Factor out the greatest common factor.
Okay, so in the one on the left, what is it?
X squared.
Leaving?
X minus 3.
And the one on the right?
9. Yeah, 9. Then it would be x minus 3.
As long as these two things are the same, then you're in good shape to group. So what's the next step?
X squared plus 9. And x minus 3.
I'm going to put the x minus 3 first, because that's the common practice when you're factoring stuff out, is to put the thing that you're factoring out first. Leaving x squared plus 9, is that an irreducible quadratic?
No. X plus 3 and x minus 3.
Is this number always positive? This number right here. If it's always positive, it's an irreducible quadratic because it's never 0.
Okay.
If you can't make this quadratic 0, then it has to have complex solutions.
So
that is our final answer. That answers number 4 perfectly. It's got one linear factor, and it's got one irreducible quadratic.
Okay.
Now, to answer, write the function as the product of the linear factors means they want you to break it all the way down. In other words, not just to an irreducible quadratic, but to the linear factors that make up that irreducible quadratic. What are they? Not
X plus 3i.
there you go. It's x plus 3i and x minus 3i.
But explain linear to me exactly.
Linear means the x term is only to the 1 power.
Okay.
Up here, that's linear, but that's not. The x is squared. So that's a quadratic. Linear also means if you're graphing it, it's a straight line. X minus 3 graphs as a straight line. Quadratics graph as curved lines. Cubics graph as curved lines. So there's a lot to be said for getting something down to its linear factors. For one thing, we find the zeros. Of course, we know the only, what's the zero of this function? How many zeros are there?
3.
It's only 1. Remember, complex linear factors do not produce zeros.
So it would be 3.
It will only cross the x-axis at x equal 3. The other two factors won't. That's why a lot of times you reduce it down to an irreducible quadratic, because keeping factoring this down to this doesn't show you any more information, really. It doesn't show you any other zeros. So what's the point of doing that? List all the functions zeros, there's only one. X equal 3.
Okay.
Perfect timing. Taylor?
Thank you.
Thank you, and thank you for answering those questions on my email. That tells me that I can kind of get away with doing that once a week.
And my mom also added 150 to my account as well.
Okay.
Okay, have a good night.
You too, Taylor.
Okay, thank you.
Bye-bye.